Good morning, everybody. Now we shall discuss on session 8 from the first unit, that is laws of motion, for the first semester students, in which the title of the program is for the mechanics. Here we are going to understand the Newtonian mechanics, frames of references, relativity and dynamics of particles of system. Let us see the recap of the previous class. In the session 7, we have studied about the transformation equations for a non-inertial frame of reference. Here we are going to learn the rotating frame of reference, in that Coriolis acceleration and the force. From this session, we are going to understand the rotating frame of reference, in which we are going to know the Coriolis acceleration and the force. To understand about this session, we need to have the basic knowledge about the frames of reference, important concepts, some of the terms, Newton's laws of motion and its limitations, inertial frame of reference, concepts of absolute space, time and motion. Even we should have the idea about the Galilean transformation equations and also the transformation equations for both inertial frame of reference and non-inertial frame of reference. So here, once again let me repeat, a non-inertial reference frame is a frame of reference that is undergoing acceleration with respect to an inertial frame. As we all know, in all inertial frames, the laws of motion are the same, whereas in the case of non-inertial frames, these laws vary from frame to frame depending on the acceleration. A rotating frame of reference is a special case of a non-inertial reference frame, that is rotating unit vector. In a rotating coordinate system, a free particle moves in a way that appears to be affected by three forces. So what are those three forces? The centrifugal force, the Coriolis force and the Euler force. A rotating frame of reference is a special case of non-inertial frame of reference, that is rotating relative to an inertial frame of reference. A good example for rotating frame of reference is the surface of the earth. Rotating reference frames are characterized by three forces, as already I have told you now: the centrifugal force, the Coriolis force and the Euler force. Coriolis acceleration is the acceleration. We all know acceleration is the rate of change of velocity. This is also a acceleration, and this acceleration is due to the rotation of the earth experienced by particles moving along the earth's surface. Coriolis acceleration is generated by the eastward rotation of the earth around the north-south axis. And this acceleration is named after a scientist. He was a mathematician, and this scientist analyzed the fictitious forces that are present in a rotating frame of reference. The Coriolis acceleration is a function not only of the rotational speed of the earth but also the relative fluid velocity. From a rotating reference frame, any object which is in motion will be influenced by the Coriolis force, and its strength depends on only a few variables and the relative direction of their vectors. Now this Coriolis force is given by minus 2m and the product of these two quantities, and from this Coriolis force is nothing but it is a fictitious force which is causing the apparent deflection of moving objects when viewed in a rotating frame of reference. The effect of the Coriolis force is an apparent deflection of the path of an object that moves within a rotating coordinate system. The object does not actually deviate from its path, but it appears to do so because of the motion of the coordinate system. Let us summarize about this session now once again. A non-inertial reference frame is a frame of reference that is undergoing acceleration with respect to an inertial frame. And in all the inertial reference frames, the laws of motion are same, but whereas in non-inertial frames, these laws will vary from frame to frame depending on the acceleration. A rotating frame of reference is a special case of a non-inertial reference frame, that is rotating unit vector. In a rotating coordinate system, a free particle moves in a way that appears to be affected by three forces. So those three forces are the centrifugal force, the Coriolis force, and the Euler force. A free particle considered from a fixed and a rotating set of coordinate axes. And this rotating frame of reference, it is a special case of non-inertial reference frames. A non-inertial reference frame is a frame of reference that is undergoing acceleration with respect to an inertial frame. Like for example, an accelerometer which is at rest in a non-inertial frame will in general detect a non-zero acceleration. Here, these rotating reference frames are characterized by the three forces. Those three forces are the centrifugal force, Coriolis force, and the Euler force. In a rotating frame of reference, objects require a centripetal acceleration to remain stationary in that frame. And the moving objects in rotating frames move in curved paths due to the Coriolis acceleration created by the fact that the velocity of points in the frame are greater further from the axis of rotation. Rotating and accelerated frames of reference are non-inertial. Means example for non-inertial frames of reference is a rotating frame is a non-inertial, as well as an accelerated frame is also a non-inertial. And the three forces which comes in the rotating frames are the fictitious forces, such as the Coriolis force. And so we are now studying about the Coriolis force, which comes under the fictitious force in the case of non-inertial frame of reference, which is for which we can take rotating frame as a good example for the non-inertial frame of reference. So Coriolis force, we can apply Newton's second law of motion in a rotating coordinate system to an object which is at rest, and with respect to that rotating frame, by including the centrifugal force, which is an apparent force. If the object is moving with respect to the rotating reference frame, an additional apparent force is required for Newton's second law to be valid. And that required force or the required additional apparent force is nothing but the Coriolis force. Then about the Coriolis acceleration. Whenever a point is moving on a path and the path is rotating, there is an extra component of the acceleration due to coupling between the motion of the point on the path and the rotation of the path. This component is called Coriolis acceleration, and Coriolis acceleration is equal to 2 omega v, and this is normal to the radius and it points towards the left of an observer moving with the slider if rotation is counterclockwise. If the rotation is clockwise, it points to the right. In physics, the Coriolis force is again a fictitious force that acts on objects that are in motion within a frame of reference that rotates with respect to an inertial frame. In a reference frame with clockwise rotation, the force acts to the left of the motion of the object. The effect of the Coriolis force, it is an apparent deflection of the path of an object that moves within a rotating coordinate system. The object does not actually deviate from its path, but it appears to do so because of the motion of the coordinate system. Then we'll see the applications of this Coriolis force. It is for the movement or flow of air across the earth. So consequently, an object which is moving above the earth in a generally northerly or southerly direction and with a constant speed relative to space will be deflected in relation to the rotation of the earth. Now after this we will solve some of the questions. The first question is, Coriolis component of acceleration exists whenever a point moves along a path that has non-inertial frame of reference. And answers for this: A. Tangential acceleration, B. Centripetal acceleration, C. Linear motion, D. Rotational motion. So what will be the answer for this question? Answer D, that is rotational motion. Next, second question. When an object simultaneously rotates about a point and moves relative to that point, it is called an which acceleration? It is called an Coriolis acceleration. That is option B is correct. The third question. The Coriolis effect is a result of what? Option A, pressure gradient. Option B, Earth's axis of inclination. Option C, Earth's rotation. Option D, Earth's revolution. So the answer for this question, that is the Coriolis effect, is the result of Earth's rotation. Hence, option C is correct to this question. The fourth question. Coriolis component of acceleration is a component of translatory acceleration. Whether it is true or false? Yes, it is true. Coriolis component of acceleration is a component of translatory acceleration. So answer to this question is A, which is true. And these are some of the references. You may go through these references to understand the session 8 on laws of motion. Thank you one and all.